Hi friends, today I am introducing a new lecture on elementary signals from Jnana Learning. So, there are several elementary signals which play vital role in the study of signals and system. And these elementary signals serve as the basic building blocks for the construction of more complex signals. The elementary signals may be used to model a large number of physical signals which occur in nature. So here I am introducing the elementary signals. First one, exponential signal. Second one, sinusoidal signal. Third one, unit step signal. Then the unit impulse signal and unit ramp signal. Okay, so these are the important elementary signals. So we move on to the first elementary signal, that is exponential signal, and we have continuous time exponential signal and discrete time exponential signal. First we are considering the continuous time. So the general expression for a real exponential signal is given by x of t is equal to a e raised to bt, where a and b are real parameters. The parameter a is called the amplitude of exponential signal measured at t is equal to 0. Now based on the nature of values of b, we have growing exponential and decaying exponential. That is, if the value of b is greater than 0, that particular exponential signal will be growing type, that is a growing exponential signal. And the value of b is less than 0, then it will be decaying exponential signal. So here shown the growing exponential signal and decaying exponential signal, that is when the value of b is positive, that is if b is greater than 0, then it will be a growing exponential signal as shown in the figure, and when the value of b is less than 0, then the exponential signal will be decaying type as shown in the figure. Now we are considering the exponential signal in discrete time. So here the general expression for a real exponential signal is given as g of n, which is equal to a small a raised to n, and where a small a is equal to e power alpha for some particular value of alpha. And here also we have the growing exponential and decaying exponential. So the growing form of discrete exponential signal is defined for small a greater than 1, and the decaying form of discrete exponential signal is defined for 0 less than a less than 1. So here shown the decaying exponential signal and growing exponential signal. So the decaying exponential or decreasing exponential signal is defined for 0 less than a less than 1, and the increasing exponential signal or growing exponential signal is defined for the values for small a greater than 1. Okay, so that's about the exponential signal. Next we move on to the second type of elementary signal, that is a sinusoidal signal. So here also we have continuous time sinusoidal signal and discrete time sinusoidal signal. First we are considering the continuous time. So the general expression for a continuous time sinusoidal signal is given by x of t is equal to a cos omega t plus theta, where a is the amplitude of the signal, omega it is the frequency in radians per second, and theta is the phase angle in radians. So a sinusoidal signal is an example of a periodic signal. Okay, and the period is defined as capital T is equal to 2 pi by omega, where omega is the frequency of the signal. Okay, so here shown the continuous time sinusoidal signal, amplitude and wavelength are marked over here. So this is the continuous time sinusoidal signal. Now in discrete time, the discrete time sinusoidal signal is expressed as x of n is equal to a cos omega n plus phi, where a is again the amplitude of the signal, omega which represents the angular frequency, and phi it is the phase angle. Okay, so Not all discrete time sinusoidal signal with arbitrary values of omega are periodic, and also the angular frequency omega must be a rational multiple of 2 pi for a discrete time sinusoidal signal. Okay, so as shown in the figure, the discrete time sinusoidal signal will be defined for the discrete values, and the particular discrete time sinusoidal signal will be as shown in the figure. Now we move on to the third elementary signal, that is a unit step signal. Okay, so a unit step signal or a unit step function is a type of elementary function which exists only for the positive side and is 0 for negative side of the time axis, and it is discontinuous at t is equal to 0. Okay, so here also we have continuous time unit step function and discrete time unit step function. So the continuous time unit step function is denoted by u of t, and it is defined as u of t is equal to 0 for t less than 0 and 1 for t greater than 0. Similarly, the discrete time unit step function is denoted by u of n, and it is defined as u of n is equal to 0 for n less than 0 and 1 for n greater than or equal to 0. Okay, so that's about the unit step function or unit step signal. So here shown the continuous step signal and discrete step signal. So as discussed earlier, the continuous step signal will be defined in such a way that for t less than 0 the value will be 0 and for t greater than 0 the value will be 1, and in discrete case for n less than 0 value will be 0 and for n greater than or equal to 0 the value will be 1. Okay, so that's about unit step signal. So next one, that is a unit impulse signal. So here also an impulse signal is defined for continuous time and discrete time. So the continuous time unit impulse function is denoted by del of t, and it is defined in such a way that del of t is equal to 0 for t not equal to 0, and integral minus infinity to infinity del of t dt will be equal to 1. And this del of t is also called as Dirac delta function. Now in discrete time, the unit impulse function is denoted by del of n, and it is defined in such a way that del of n is equal to 1 for n equal to 0 and it is equal to 0 for n not equal to 0. Okay, so that's the unit impulse function. Okay, so here shown the continuous time impulse signal and discrete time impulse signal. Continuous time signal, that is del of t, and discrete impulse signal, that is del of n, which is having value 1 for n equal to 0 and 0 for n not equal to 0. Okay, so that's about the unit impulse function. Next elementary signal, that is a unit ramp signal. Okay, so the continuous time unit ramp function is denoted by r of t. It starts at t is equal to 0 and increases linearly with time t. Okay, so the nature of the ramp signal will be an increasing linear with time t. So it is defined as r of t is equal to 0 for t less than 0 and t for t greater than 0. Okay, and in discrete time the unit ramp function is denoted by r of n, and it is defined as 0 for n less than 0 and n for n greater than 0. So here shown the continuous ramp signal and discrete ramp signal. So from the figure it is clear that for continuous ramp signal, for t less than 0 the value will be 0 and for t greater than 0 the value is according to t. Okay, that is the ramp function. And for discrete ramp signal also, for n less than 0 we have values 0 and for n greater than 0 the value or the amplitude of the ramp function is n. Okay, the value of n will be the amplitude of the ramp signal. Okay, so that's about the unit ramp function. So we have discussed all the elementary signal, and there are some relationship between these elementary signals. and it is very important to know that relationship for solving many problems in signals and system. Okay, so here I am introducing the relationship between step signal, ramp signal and impulse signal. First, relationship between unit step and unit ramp function. So the relationship is in such a way that d by dt of r of t, which is equal to u of t. R of t is the ramp function and u of t is the unit step function. And when we integrate u of t, or when we integrate the unit step function, we get the ramp function. Okay. Next is the relationship between unit step function and impulse function, that is d by dt u of t is equal to del of t. U of t is a unit step function and del of t is a impulse function. And when we integrate del of t, or when we integrate the impulse function, we get the unit step function. And relationship between unit ramp and impulse function is in such a way that double integral del of t dt is equal to r of t. That is, a double integral of impulse function is unit ramp function, and d square by dt square r of t is equal to del of t. That is the impulse function. Okay, so these are the relationship between the step function, ramp function and impulse function. It is very important to know these relationship in solving many problems related to signals and system. Okay, so that's about the elementary signals and their relationship. So thanks for watching the video. Hope that the video is informative. For watching more informative videos, please subscribe our channel Jnana Learning. Thank you so much.